Mm-hmm.
It moves above the ground with a velocity of 10
meters per second.
When does the ball hit the ground?
All right. So this particular example I was not fond of, but I thought I could salvage parts of it for the purposes of our notes. So let's try to make a sketch of what this would look like. So I want everyone, just right above that problem, to draw some axes. My independent variable is time, right? And then what's the dependent variable? What are we going to measure if we're throwing a ball straight up in the air?
The meters.
The distance, right?
Yeah.
The distance. All right. So, if I throw a ball straight up, so that's like, just like that. Exactly. Like you're holding a ball like this and you just throw it, right? Just throw it. Right up. You just throw it, right? Straight up. You're holding a ball and you just throw it, right?
Why would you throw it?
Why don't you go like?
You're just throwing it straight up in the air. It doesn't matter how. So does the ball start at the ground?
No.
No.
In your hand.
It's going to start in your hand. So it's going to start like right here, right? That's 3 meters. And when the ball leaves your hand, what's going to happen to the ball? It goes up. And then eventually, whatever goes up must come down, right? So it's going to go up and then come back down. And then what happens to the ball?
It falls to the ground.
It falls and hits the ground, right?
Once you catch it, go
We're going to assume for today's purposes that we just like toss them and then let them fall. Okay? That's it, right? So what shape does this look like?
Almost like you.
And it's almost like a U. What mathy word did we use last week to describe that U or the N? Parabola. This is an upside down parabola, right? It did. Lots of brain power. It's an upside down parabola. Is it missing parts?
Yeah.
Yes.
Normally we'd keep going, right? But let me ask you this. Can I have a negative time?
No, you cannot.
No. Can we have a negative distance?
Unless you're on the ground.
All right. Ooh, let's talk about this. I want to talk really quickly about, excuse me, about distance and positive and negative distance. So I'm in my house, right? Imagine me standing in my house. I go outside, and I turn to the left, and I walk down the sidewalk. Am I walking a positive or negative distance? A positive distance away from my house, right? I'm going away from my house. What if instead of turning left, I turned right and walked right down the sidewalk? It's still a positive distance, right? Because I could walk 1 block away from my house, 2 blocks away, right? What if I came out and I turned and I walked backwards away from my house? Is that a negative distance?
No, you're still going the same way.
No, so you're still going to go the same distance. I'm just walking funny, right? I'm just walking away from the house, exactly. Right? All right, so let's think of it this way. Let's think of it this way. Have you ever held a pebble like over a lake or a river and dropped it? Like a rock? Because it makes that fun plunk, right? And then you get to if the water's really clear, then you get to watch it like sink all the way to the bottom. Right? It's kind of fun. So think about the height. I want you to think about the height of that rock. So if you're standing like on a bridge or something and you drop the rock, what's happening to that distance to the surface of the water? Is it getting positive or negative? It's getting closer, so it's decreasing, right?
Wait, I thought you said what it gave. Oh, yeah.
All right. So it's getting closer and closer, right? And what happens when it hits the water? It's at 0. Does the rock just stop?
No, it goes negative.
It's going to be negative below the water, right? It's going to be a negative distance below the water.
So above the water
It's positive. Below the water would be negative. If we were talking about like at sea level or water level, right? So what if, because someone brought this example up earlier today, what if, have you ever been to like the Grand Canyon or like a big, trying to think, Big Bend. Big Bend has a big cavern. The Grand Canyon, Natural Bridge Caverns, that one too, because it's a hole in the ground, right? What if you dropped a rock off into that giant hole? Would your distance be positive or negative? It'd be negative because it's below the ground, right? It's below the ground, right? So here, let's think about this problem. What kind of ball do you think that we're throwing here? A baseball, a tennis ball, a football, right? So a bouncy ball. And if it's a bouncy ball, we're just measuring that first time that it touches the ground, right? It might bounce some more, but we're not going to worry about it. We want to know, when does it hit the ground the first time, right? So what's going to happen to that ball when it hits the ground? Is it going to go through the ground at all? No, right? No. What if I threw a bowling ball like that? It would make a dent, so we might have a little bit of a negative distance, right? Okay. So I just wanted to talk a little bit about positive and negative distance. Let's move on to example. So take a look at the right of your paper. To the right of your paper. Example 2. Let's see. Natalia, can you read example 2 for me, please, dear?
A student mother, father, driving them back to school. Along the way, the student realizes they left their backpack at home.
Mm-hmm.
The table of the values tracks the time since they originally left the house versus the distance of miles they are from their house.
Beautiful. Thank you, dear. So my time is X. My distance is Y. So let's just kind of read through this table. You looking at your table? Let's kind of read through this table. So after 10, they don't give me units. So what should I say my units are? Are we going to measure in seconds, minutes, hours, days? Seconds. So after 10 seconds, we've gone 5 miles.
10 minutes.
Let's say minutes is a safe assumption. Okay. So after 10 minutes, we've gone 5 miles.
You mean an hour? You should do hours because you can't really do that.
No,
that makes sense.
Why would you go to hours? Why would you go to like school?
Yeah.
10 hours.
There we go. So after 25 minutes, we've gone 10 miles.
I can't.
After 40 minutes, we've gone 15 miles, right?
Yeah.
After 55 minutes, we're 10 miles from home.
So you're going back.
Oh, so we turned around and went back, right? So what's it safe to say about this point here?
That's their turnaround point.
That's the turnaround point. That's the point where you realized, uh-oh, I forgot my backpack, Mom. We got to go back.
I'm so dumb.
I'm on the paper.
All right. So then at 70 minutes from the time we initially left the house, we're 5 miles from home, right? All right. So what we're going to do is we're going to take this data here and we're going to plot it on this graph. So we were just talking about positive and negative time and distance.
Yeah.
So here, if we're talking about leaving our house and coming back, are we going to have a negative distance?
No.
No. Are we going to have a negative time?
No, we can't have.
No. But I put those axes right there in the middle, didn't I? Could I move them over so that I have a little more space to graph?
Yeah.
Yeah, let's do that. So what I want y'all to do, I want you to redraw your axes all the way to the left and all the way to the bottom. All right. So, time are my x values, so let's label time down here at the bottom. And we decided to label this in minutes, right? Is what we decided? So, what's my biggest time value? 70. So can I count by ones? Do I have 70 boxes? No. Fives? 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. So we'd have to count by tens, right? So let's count by tens. We have 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Is that okay? excuse me. So what about y? What should I label that y-axis? Well, not what we're going to count by, but first let's label it.
5.
What is the y counting? The distance. Distance in miles. Beautiful. All right, and then what's my biggest y value? 15. So what should I count by?
1.
5.
Let's see. If I count by ones, do I have enough?
No.
5.
So let's count by twos. So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20.
2, 4, 6, 8.
I did. I just labeled every other one because I wrote kind of big.
Oh.
If you write smaller, you can label every box, every line. But I know I wrote kind of big.
Wait. 2, 4, 6, 8.
So now let's plot those 5 points that we've got. We've got 5 data points from our trip to and from school, right? So the first point is located at 10, 5. Making sure you're awake.
Yeah, I'm awake.
Okay. 10, 5. So I'm going to go over 10 and up 5. Ooh, so I'm going to have to go halfway between 4 and 6, right? Because I don't have a 5. So halfway between 4 and 6 is right about there, right?
Yeah.
Okay. Then I've got 25, 10. 25 is halfway between 20 and 30.
It's a pyramid.
All right. You ready?
Yeah.
Then I've got 40 and 15. 15 is halfway between 14 and 16. And we said that that was our turning point, right? So we're going to come back down to 55 and 10. And 70 and 5. And it says draw the best fitting parabola. So we're going to sketch a parabola. So should I draw straight lines from each point to each point? No, because a parabola is it straight lines or is it a curve?
Curve.
Curve. So let's try to make our parabola kind of curvy. Like that? Yes?
Oh, yes.
I'm going to scoot up just a smidge here. All right. So I want to estimate the coordinates of the zeros for this parabola. So where are the zeros located? Where am I going to look?
You can look at the back.
At the back?
Wait.
It's where it crosses the x-axis, right?
Yeah.
So I'm going to look at the x-axis here.
50, 50, 50.
We've got 0, 0,
And then 85.
and 80. Well, it could be, I got 80, but if you got a little more to the right, 85, right? I'm going to put 80 because that's where mine fell. Yes? All right, that last question, I don't like. We're not ready for it yet. We're going to do that after spring break.
Bet.
Let's bet. I'll win that bet. No, we're not done. Go back. I'm going to change the question. We're not going to waste it. Psh. So we're going to find the domain for this data. So, help me out, you guys. What's my domain? So that's the x values. Beautiful. That's the x values, right? Samantha, what's my smallest x value? What's the small? Well, what is x representing? Time. What's my smallest amount of time? Where do we start? 0. So I'm going to say 0 is less than or equal to, and we said domain were the x values, right? X is less than or equal to. So here I said, well, 0 was when we left the house, right? When did we return to the house?
At
80. It's less than or equal to 80.
It took 80 minutes?
Yeah.
To walk. Hold up.
That's an
To
hour
drive.
and 3, an hour and 20 minutes.
45,
An hour and
45 miles. Or 45
Uh-huh.
miles.
You know what? And then the time that the kids.
Maybe there was a lot of traffic.
What by tomorrow?
45
It's gonna be
miles.
late.
All right.
For a trip.
Flip your notes over. Let's take a look at the next side. Let's see. Donnie, will you read the next example for me about Lewis?
Lewis kicks a soccer ball. The graph below shows how the ball over time.
Beautiful. So let's take a look at this graph because my numbers got kind of muddled. So Lewis kicks a soccer ball. Normally when you kick a soccer ball, where is it?
Straight.
Initially, it's on the ground, right?
Oh, yeah.
Oh, I've got an expert here. I've got an
Let's
expert.
keep it in the air.
Oh, unless I kick it in the air. That's the next question I was going to ask. Because could I kind of toss it up and then kick it?
No, miss. When someone hits it,
Yes,
you
you
got,
can.
like
Right.
in the air.
But like if I'm practicing that, right? If I kind of toss it up and then like run and kick it?
We have
Not that I
another
would do that.
expert.
Not that I would do that. I wouldn't be able to do that. One of you ladies would have to demonstrate for me. One of y'all would have to demonstrate for me.
I can do it too.
But if that were the case, where would my y-intercept be? Would it be here at 0?
No.
No, it would be further up somewhere, right?
Yeah.
Very good. Okay. So, I just want to make sure that we see it where everything is. So we've got, this is 10, 20, 30, 40. Sorry, my numbers got kind of skewed. Can y'all see where they're supposed to be now? Okay. You ready, Miss Mariah?
Yeah.
All right. So my ball, we kick the ball, what goes up?
Goes down.
Must come down, right?
Oh.
Especially when we live on Earth.
Yeah.
We've got gravity, you know.
Unless
All
you're
right.
in space playing soccer.
Well, no. We're gonna play soccer on Earth.
On Earth.
So Donnie, what does number 1 say?
What conclusion about the path of the ball can we draw from the graph?
All right. So we were just talking about this graph a little bit. Preston, what can I say about the path of this ball? What's going to happen to it?
It's gonna get higher.
It's going to go up, right? So it goes higher, and then what happens?
It, like the thing goes wider.
No, the ball. This is the ball. So as time is going on,
It goes up and then it falls down.
so the ball goes up, then it falls down. So the ball goes up, then falls back down. All right. Number 2, Preston, can you read number 2 for me?
The x-axis represents the number of blank that have passed since Leslie kicked the ball.
Whoa, are we paying attention? Who initially kicked the ball? Lewis.
Lewis.
But now I say Leslie. That's just a typo. So that should say Lewis.
Are these
So
on your
Adriana.
website?
You'd be on the other side. So the number of what that have passed? So what are we counting the x values in?
Seconds?
Seconds. Thank you, Adriana.
I said it.
You'll be next. You ready? So the number of seconds. All right. Number 3, Adriana, can you read number 3 for me? It's on your paper.
The y-axis represents the blank of the ball in feet.
Ooh, so the y-axis represents, can you answer that for me? The height of the ball. Beautiful. All right, Miss Mariah, can you read number 4 for me?
I'll read it.
No. It's Mariah's turn.
What are you doing?
No, I'm waiting. No, that was not you. I'll come back to you.
I can
So-
volunteer for her.
No. Alright, so how many feet above the ground does this ball start at? We said 0, right? So this particular ball was on the ground when we kicked it. 0 feet. Matthew, can you read number 5?
2. The ball reaches a maximum height opportunity.
Of approximately. You got it.
Approximately, we're about to answer that.
No, you can say blank.
Blank feet after blank seconds in the air.
Alright. Miss Samantha, can you help me with this part?
I don't know.
I'm gonna help you. So if it says reaches a maximum height, what am I looking for on that parabola?
Maximum height.
The maximum height, right?
Yeah.
So, Samantha, where is the maximum height? So we're looking for the vertex of that parabola, right? Where's the vertex?
Oh, that's 10.
Uh-huh.
0, 1.
There we go. So, so what's my x value? So if this is 1, 1.5, so 1.5, comma, and that looks like it's just below 40. What's the number just before 40?
30.
I would say 39.
You messed up.
39. There we go. That's okay. All right, so let's see if we can answer number 5 now. You ready?
Yeah, are you ready?
So it says the ball reaches a maximum height of approximately blank feet. So how many feet above the ground is the ball at its tallest? 39. After how many seconds? 1.5. Beautiful. All right, number 6. Number 6. Yes, are you ready? Can you read 6 for me?
The ball returns to the ground. Yeah, that's what the teacher said. The ball returns to the ground after blank seconds in the air.
All right, so for how many seconds was the ball in the air?
30. 9.5.
Well, that's when it reached its max, right? So 3 total seconds. Look, look, look. So from 0 to 3, that ball's in the air, right? So 3 total seconds. 7. 7's kind of tricky. Baylor, can you read 7 for me?
How long was the ball at least 20 feet off the ground?
Beautiful job. So I want to know, for how many seconds was it 20 feet off the ground? So this is what I'm going to do.
For 20 seconds, it was 0.5.
So I'm looking, how long is it 20 feet or more off the ground?
0.5.
So from
For a second.
0.5 to where?
To 2.
2.5.
20. Wait.
So how long is it from 2.5 to a half?
3.
So if I subtract
Then 2.
2 seconds. Two seconds.
Oh! She needs some help.
All right, number 8. Number 8. Lexi, can you read 8 for me, please?
What is a reasonable domain and range for this problem situation?
Beautiful job, thank you. So my domain, is domain the x values or the y values?
X.
The x's, right? So if I look here, Between which two x values is this function true?
1 and 3.
Between 1 and 3, so it starts right here.
0 and 3.
Oh wait, 0.
0 and 3. So to say between 0 and 3, I'm going to say 0 is less than or equal to, and domain describes the x's, right? Is less than or equal to 3. Yes? All right. What about the range?
It's the Y.
Though that's the y's. So between what two y values?
0 and 39.
0 and 39. So my range is going to be 0 is less than or equal to y is less than or equal to 39. All right. The right side of your paper, there's a problem there at the top about throwing a stone, but my graph did not come out the way I thought it was going to. So we're going to skip that problem for now. We're going to come back to that one. I want you guys to take a look at the last problem. Let me see.
Are you lying?
You'll read? Vincent, can you read about athletic atom for me?
Athletic atom threw a ball straight up with an upward speed of 40 feet per second. His hand was 8 feet above the ground when he released the ball. Write a function that models the path of the ball. Use the formula h equals negative 16t squared plus 40t plus 8.
Beautiful job. Thank you. So, in our first example, we had a table, right? In our second example, we had a graph. So in this third example, we have an equation, right? So what can I do with this equation so that I have some of the same information we had before? We could graph it. So if you graph this in your calculator, what do we have to change?
T's.
The t's to what?
To the X.
To x's. So be sure that you guys change those t values. Oh, I should have done that. Not in black. Let's do blue.
And the H there.
Oh, biscuits and gravy.
Biscuits.
So our t's are going to be x's, right? That h, that's your f of x, right? That's already in there. Or you could change that to y, right? All right, I'm going to give your group about 5 minutes. I'm going to give you all about 5 minutes. I want you to graph this, and then we're going to check it together. Okay?
Yep.
Okay, so we used our calculator to find a few special points. Oh, this one was 0, 0, 8. To find a few special points. So I want to know, how long was the ball in the air? Donnie, put your phone away. How long was the ball in the air? Well, look here, how long, that's time. Time is going to be our x value, right? So from 0 to 2.69, right? So for 2.69 seconds, right? It says, what was the maximum height of the ball? So what was the highest the ball got? 33 feet, right? And how long did it take for the ball to get to that 33 feet? So, because we released it there, so 1.25 seconds.
How did you get 1, 2.5?
We found the maximum, the vertex in our calculator. 18 says, after it reached that maximum height, how long did it take it to fall? 2.69 minus what? 1.25. What'd y'all get?
I'll do it.
1.41.
I got 1.44.
1.44 seconds. And finally, what's a reasonable domain for this situation? Less than or equal to x is less than or equal to what? What's my biggest x value? 2.69. There we go.